Hello everyone, we are going to cover HLASM high level assembler language. This is the assembler language that is used in IBM mainframes. We are going to have a 6 to 7 classes and we will have a separate recording for each one of them. This is class 1 where we are going to talk about mainly the GOS architecture that is relevant to assembler language, and as we proceed we will keep picking up one topic in each class and cover the entire HLASM. Okay, let's move on. So what we will cover: first class we will cover introduction to GOS architecture, then we will cover various data types, integers. We'll spend a lot of time and loading and adding, that would be the class 2. Again, integers, multiplication and division, which is going to be the class 3. Then we will talk about characters, and then we will talk about the packed decimals. This itself will take quite some time, and we will be able to cover most of the base concepts. Then we will spend some time on branching and looping, and we will go into putting all together. So we will go through a couple of programs where whatever we have learned in the previous classes, we will see how it is really works in a program. This is by any chance not a comprehensive course, but good enough for you to start. In fact, it will cover quite a bit of material. What we are not covering here is file handling. If I get a time, I will put a separate class for that. But this course should be sufficient enough to get a good hang of the subject, and if you want to learn any further you can do yourself, or I will spend some time later and create a course that is for few more topics which are in my mind, including file handling. So the very first question you will get is, why am I even learning this? You are learning this, maybe a simple answer is your company asked you to learn. But why your company is asking you to learn? Because this is still in use and somebody is using for their transactions. Who are using it? Your banks, your airline companies, insurance companies, retail companies, and many more, many more. So then why are they using it? Why they didn't replace it? There are two fundamental reasons. First reason is that its efficiency. It works very close to the CPU. It is very fast. It is very reliable and stable. Some of these programs are running all the way from 1960 or 1965. So you are a program that is running from last 65 years. Okay, and it is a full control over memory. So it is directly talking to the memory. So something is reading and writing into the memory. So it is very efficient. Every time you have done, let us say, a particular credit card transaction, there is a good chance that somewhere the last bit of the transaction is happening in assembler, where what we call is where rubber meets the road, or behind all the beautiful jazzy screens of airline companies, or nowadays even you are using a chatbots, maybe a ticket is getting booked in the end by a assembler program in the last layer of the structure. As I said, it's very efficient. Beyond that, there is one more reason, that is called backward compatibility. What is it? Every time if you have a lot of programs, if you have a phone, you would have seen that after some time the app has to be upgraded, and sometimes the phone itself will say, oh, I can't upgrade my operating system anymore, move on, you have to buy a new phone, or you have to live with the old operating system and the old apps. Instead, what IBM has done is it implemented the backward compatibility. That means every time I upgrade my operating system, I ensure that the old programs are running as it is. They are not becoming defunct after some time. Some programs may be written in 1960 are running today. So you don't have to rewrite these programs when I upgrade my operating system. And that is also one of the reasons, apart from the, of course, the efficiency you cannot rule out, apart from the efficiency, this backward compatibility, both put together making these assembler programs even run today. So let us go ahead and learn the subject. So what is mainframe assembler? It is also known as HLASM, high level assembler language. So this is the last software layer that works with G system hardware. Though we are calling it as the last software layer, if you notice, we are also telling this is a high level assembler language. What it means is that if you write a assembler language program or macros and you try to run it, you won't be able to run it. You still have to compile the program, which will give you an object module like any other program. Then you have to link it. It will give you load module like any other program. And the load module is what is really interacting with the operating system, and that is one is running. So if I can call the load module as, let us say, point 0, where rubber meets the road, what we call, maybe HLASM stands somewhere like point 2 or point 3, a little couple of steps above. So we need to still compile the program, we still need to load the program. That's why we call it high level assembler language. What it does, as we spoke in our previous slide also, it provides direct control over CPU registers and main storage, which we will quickly see in the below program. Here, you're not programming the code, you are programming the machine. What does it mean? When you write a Python program, when you write a COBOL program, not many times you will think about, oh, how this hardware is going to be. You will still define the variables, and maybe some event happens, you will analyze it. But many times you are not thinking about the machine itself. Here, what you are doing, you are actually talking to the machine, and you are directly programming the machine itself. It's a very powerful macro programming language, which we have also spoke about in the previous slide. And also it is a very structured programming language. Like if you want to look at more rest of the 4GLs also will look like this. So it's a very structured programming. I thought at this point, let me show you a small snippet of the code, which will make you understand what we are talking about. Let us look at the simple three statements. L R1 num1. What we are doing, there is a variable called num1, which is value is 10, and we loaded that value into a register called R1. So num1 became 10 became R1. If I want to write in a regular programming language, I would have simply done R1 equal to num1. Then what I'm doing, I'm adding R1 and num2. Num2 is 20. So if I add 20 to my R1, it will become 30. In everyday programming language, I would have written as a R1 equal to R1 plus num2. Now my R1 is consisting 30. I'm storing back it in my result. So st R1 result, taking the value of R1, it is putting back in a variable called result, which I will use it later. So result equal to R1 if I want to use a everyday programming language. If you really look at, you will think, oh, this is very simple stuff. This is what we do all programming languages, and looks like some syntax is different, otherwise it is same. No, first of all, num1 and R1 are not same. Num1 is a variable sitting in your storage, and R1 is a register. Think like that for a minute. And these two behave very differently. This program, what we are showing here, we will use it again and again and again, and it's like, you will start realizing how much depth is there in these three simple statements, and so much of inside functioning is happening just to execute these three simple innocent lines. So I don't want to scare you, but at the same time I also want to tell that don't get fooled saying that, oh, this is looking a very simple. I have done so many different kinds of programming languages. It looks like one more programming language, unless and until you have done a hardcore assembler in any 80, 85, 80, 86 or anything, it will make more sense to you. So we will expand, we'll keep expanding this program as we go forward in this particular course material. But this is how it looks like. L is a load, which is nothing but, like, say I take value num1 and put it in R1, then I just add the value and I copy back the value. This is a small snippet of the code. Look into this and we keep expanding in all the next slides. Since we are all familiar with regular GUI system, I just want to recap one more time. If you look at where do code, load module and data reside, we all know that it is somewhere in the storage. You can call it dash D. Sometimes it is in the PDS members. When it comes to data, it could be in physical sequential files, it could be in VSAM files, it could be in DB2 tables. So the data is there on the GOS system stored somewhere. The executable code also stored somewhere, but they don't interact with each other. In fact, they don't even know that the other thing exists, right? The load module is on its own, sitting in some PDS member, and data may be sitting somewhere in a VSAM file or a DB2 file. So all are in same place, but they do not talk to each other by themselves. Someone must execute this program. How do you do it? Either you call a GCL batch job, or you use a OLTP transaction like a CSCS or IMSDC, and you start saying, okay, you load module load, then it will call data, and all those things keep happening. What is stored in the GOS environment? Your source code. For example, in our case, we are talking about HLASM. There is a source code which may be stored as a PDS member, and let us say we call that as a myproc. Within that is ASM1. Then load module is there, and when you compile this, you got a program created. Maybe that program is called myproc. Then you have a data which is physical sequential files, VSAM files, or some data is there within the program itself, right? These are all stored. Who triggers it? JCL triggers it, or OLTP transaction triggers it. It what it will call? It will call the load module, and if there is a data, maybe JCL many times also gets the data loaded along with the load module, or it provides the data to the load module. Within the JCL, it will say where the data is residing. All this gets executed in CPU, the registers, then you have a execution happening, then some PSW is getting updated, which we'll talk about it later. And while all this is happening, it is interacting with the storage. It is talking to, of course, the load module where the instructions are there. Data is there. Of course, it doesn't have to go all the way to dash D and fetch the data, because that required data always gets loaded in between. We will look into it. There are work areas and so on where the data is coming from, and data is going back to your executable program. So your instructions and your executable load data both are going to go kind of doing a to and fro from your CPU and to the storage. And maybe you have to read or write the data back. You write into your temporary storage, and from there it goes back and writes into a dash D file. So it's like this, right? A JCL, then a load module is loaded into memory. Then CPU fetches the instructions from the memory. Then CPU executes the instructions and reads or writes data from the memory and dash D. Results are returned, status is set, that is happening in the CPU, and finally program is waiting for the next instruction. The loop will continue. At some point it will say, okay, my execution is completed, everybody goes back home. This is a broad way entire our GUI system works. In fact, most of the computers work this way only. Maybe the names could be different, but more or less it works in the same way. Keep this diagram in mind. This is nothing to do with assembler. Instead of HLASM, you could have said a COBOL programmer, you could have said a PL1 programmer, a Rex programmer, something like that. Okay, let's move on. So now let us narrow it down to HLASM, that is the assembler language. This is not very different because the process is same, but I just want to show you one example. You can see this is your assembler source code, and what we have done, we added two more statements here, value 1, value 2 result. What are they doing? We are declaring the variables. At this point, don't worry about f and what is the nomenclature and what is the convention here, but just to say that there are three variables. Two variables we know the value, so we define them. Third one is what will get calculated. Initially we don't know that value. We could have initialized, but we have not done any initialization. So this assembler program gets compiled, linked, and a load module gets created. At the end of the day, if you look at the load module, it is always in this ones and zeros. So this is the machine code object program that is ready to load. Where it will get loaded, this executable code is here, the data is there, both is there in the main memory. When we say a main memory, it could be on the dash D, but actually when you run a program, there is a space where it gets loaded, which can be it accessed very quickly. It doesn't have to go all the way to your tape or all the way, it has to go into your physical sequential file. We'll talk about it, but assume that it is there here in the main story, which is easily accessible by CPU. And the instructions are coming here, some execution is happening. We will open all these boxes later, but some execution is happening. Maybe it is asking for a data, so data is coming back again from the system, from the main storage. Again some more execution is happening. After every single instruction there is something called PSW. We'll talk very detailed way about this PSW, which keeps getting updated, telling that this is where I stand, this is a kind of your log, and the process continues. Hope you understood this. It's nothing different from any other programming language. It is same process. You have a load module, you have a data, and both gets executed through your storage and CPU. Both keep interacting with each other. Okay. So in this particular course, we will concentrate on two items. One is how the storage memory works and how the CPU works. If you have learned any other programming language, let us say a COBOL or a Java or something like that, you won't have spent a lot of time trying to understand how the storage works or how the CPU works. But here it is very much required. Why it is required? Because we are directly interacting with the storage and we are directly interacting with the CPU. So it is very important for us to understand it. We are not going to cover here about the JCLs, or the what is a PDS, what is a PS, what is a VSAM, what is a IDAM. Those things we are not going to talk here, because that is a assumption is that you all know a regular mainframe. You also might know most of that what we are talking about the main storage and what we are talking about the CPU, but it is better we refresh it one more time. As I mentioned, we are going to spend time on CPU and storage. First we'll pick up storage and then we will go to CPU. So let's look at RAM and storage. You are mostly used with the terminology called ROM or RAM, but we will not use it here. We will call it RAM and storage. If you really look at here in this particular diagram, technically this is your RAM, the main storage where the data is there. It is not a permanent, it is a very volatile, and it supports the multitasking, and data is staying here, which is used by the CPU. So this entire thing is what is getting executed. That when the CPU is actually talking, it is talking to this part, not many times to this particular area, because when you want to run a program, the data is already picked up and it is already loaded here. And here is the auxiliary storage, what we call, or you can call it a storage. This is what generally in PC language you call it ROM. This is a read-only memory. This is non-volatile. This is very slow processing, and programs, executables, and data live there. So just like in a PC, you can think that way, like it is a ROM and a RAM, where actual permanent data stays somewhere, and when the program is getting executed, it will move up, it will make itself available to CPU. CPU does the actual execution. Nevertheless, how the storage is organized is similar, so we will go into it as a next slides. At this point, let me introduce this simple statement which you all know. Memory is organized in bits, and 8 bits is a 1 byte. Now let us start getting into those low level details. So let's look at a byte. What is a byte? A byte is 8 bits. That's what we just said, that a bit is the lowest unit of storage. It can be 0 or it could be 1. Sometimes we call 4 bits as a nibble, and 8 bits is 1 byte. byte is the smallest unit that is having the address. Bit don't have an address. If you have to refer to a particular bit, you will take the address of the byte and then you will add 2, 3, 4 depending on which bit you want to read from. Data and instructions are stored in memory as bytes. Everything ultimately gets stored in the system as zeros and ones. So let us look at a byte here. So it has, you can see, yes, 0 to 7, 8 bits are there. The lowest value that can be there here is 0, right? If you put all zeros, this is a 0, and if you put all ones, whatever this value is. But what happens when, for our ease of reading, many times you start looking mostly the hex values. It becomes very difficult for us to keep showing everything in the binary format. So we convert into hex format. For us is easy readability. Please remember, nothing gets told as a F or a D or a E inside the system. It is always ones and zeros at this point of time, unless quantum computing comes tomorrow, and where you can have any state between 1 to 0, and technically that is infinite number of states. Hopefully when it comes, it becomes extremely fast. Until then, let us stick to this point that the data is always stored as 1 or 0. So let us look at this. What is the minimum value? Minimum value was in a byte is 0, and maximum value, you see, 1 into 2 to the power of 7 plus 2 to the power of 6 plus all the way to 2 to the power of 0, and a maximum value that can be stored in a byte is 255. For easy reading, this is, we can also say 16 to the power of 0 and 16 to the power of 1, and we are multiplying with 15 when you're doing it with the hex format, that is 255. How do we write it in hex? If you want to write it the same value, you write it as FF. In binary, you write it as 8 ones, 1111 1111. In decimal, you write the same value as 255. This is a very important minimum concept you should know. The maximum value in a byte is 255. There are 8 bits and it is known as FF, or 2 nibbles, right? FF or 8 ones or 255. So we will go one more level deeper or wider. We just spoke about a byte. Just one small point I want to add. In the previous slide, we said that a byte maximum value is 255. We are assuming there a unsigned byte. In a signed byte, you will get 1 bit less. So there is a different range of minus 127 to 128. I don't want to confuse you, so let's keep it there right now, but we will explain all the signed and unsigned stuff later in the course. Now you look at, as I said, byte is the smallest unit and it has 8 bits. So if you start looking at the address on the topmost, a byte started at 0, then 8, 16, 24, like that. These are the number of bits. And if you really look at the address, it is at 0, 1, 2, 3, 4, 5, 6, 7, and so on. A off word is 2 bytes. So 2 bytes means basically you look at the address starting at multiples of 2. Why I am saying this, as we go further you will realize it, that a off word can only start at 2-word binary. Similarly, a full word can start at 4-word boundary, something like that. Okay, you will still start looking this kind of a nomenclature. So a off word is 2 bytes, a full word is a 4 bytes or 18 to 4, 32 bits, and a double word is 8 bytes, that is 64 bits. Remember this. I told you in one of our previous slides there is a F coming, and I said we will talk about this F. F is nothing but we are telling the full word. Based on the variable you define as a half word, full word, double word, so on, the length automatically, the space gets automatically allocated. These are the fixed spaces or fixed amount of memory address that is getting allocated the moment you say it is offered 2 bytes when it is a full word, it is going to be 4 bytes, and so on. Continuing on the same subject, I'm showing you here what is a byte, off word, full word, double word, how many bytes are there. As I said, off word 2 bytes, full word 4, and double word 8 bytes. So this determines what is the maximum value that can store. First, let us talk about the unsigned. I showed in my previous example, if bytes all the bits are 1, the maximum value a byte can have is 255. Similarly, in a off word, you would have seen 16 bits are there. So the maximum value you can have is 65, 535, and a full word is 2 power 32 minus 1. Okay, and similarly, double word 2 power 64 minus 1 if it is an unsigned value. When it comes to a signed value, you will see a min and max value. This is, if you really look at, more or less this is of the value 255 by 2, you will look like that. So minus 128 to plus 127. Similarly, off word, again off of 65 535, which is minus 32 768 to plus 32 767. It becomes very clear when you look at the full word. There you have 2 to the power of 32 minus 1. Here it is 2 to the power of 31 minus 1. So 2 to the power of 31 is half of 2 to the power of 32. And the symbol, if you put it, it is minus 2 to the power of 31. Similarly, double word, minus 2 to the power of 63 to 2 to the power of 63 minus 1. It is very important to remember these numbers because many times event happen. You for a very simple example, somebody's bank balance is 65 535, and you try to add one more rupee to it or one more dollar to it, and it becomes 65 536. And if the balance is as declared as a upward, then it will cross that particular value, overflow will happen, and the program will abort. So what is the value you can store in a offward, full word, etc.? It all depends on its size, and many times when we are doing the actual programming, we need to be very mindful of this particular ranges. Since we are going to use the hex notation a lot, let us understand a bit about binary, decimal, and hex. We all know what is a decimal value, 0, 1, 2 up to 15, and its binary values you have seen here. You all know 0, 0, 0, 0. I'm not going to spend a lot of time in trying to explain how 7 became 0, 1, 1, 1. My understanding is you know how to convert from a decimal to binary or a binary to decimal, and even decimal to hex, and vice versa. So if you look at 0, 0, 1, 1, 1, that is 0 to 7. Similarly, hex also it is 0 to 7. It starts changing from 10 onwards, right? In hexa, there's nothing like a 10, but 8, 9, A, B, C, D, E, and F. Then the 1, 0 will come, which is equivalent of 16. The data in the memory, as I told you, is always told as a binary, but it is represented in the hex for easy reading. That is why we need to understand this a bit. F0, let us say if you have seen somewhere F0 means 1 byte. Why? F is 1111, that is 4 bits, and 0 is 0000, again 4 bits. So this is one called one nibble. F0 put together is 8 bits, and its value is 240. Similarly, if you have seen C008, for example, this is a off word. Why? C0 is 1 byte and 08 is 1 byte. Keep this in the mind. The moment you saw 4 hex letters, that means you are talking about 2 bytes, because each byte is represented by 2 hex values, like either it is C0, it could be 08, it could be DE, whatever it is. So F0, similarly C0 and 08, which is offered, and it is value is 49,160. Similarly, you have a full word, which is FF, like that. 8 Fs you have. The value is 16 to the power of 8 into all the way, and 4 to whatever that value is. Okay, this is the value if it is a full word and if it is a unsigned. Similarly, same full word with a positive sign. If there is a sign is there, it works little differently. We will work out in next few slides what is the positive number and what is a negative number. But here it is 2 to the power of 31 minus 1, which is this value. If you see two hex values, it is 1 byte. So half world will have 4 hex values and full world will have 8 hex values or 4 bytes. This is how we do a notation. Keep getting used to this notation because we will use it extensively. We have seen in the previous slide how numbers are getting stored. 1 is 0001 and 8 is 1000. But when you type characters, how does it get stored? For example, you defined a variable called CL4, which is a character, and you put it in the quotes ABCD. You want to store ABCD. How A will get stored? It has a C1, B as C2, C as C3, and so on. This follows abcdic format, not a ASCII format. Similarly, small a, small b, small c, small d is 81, 82, 83, 84. Some symbols I am showing here, dollar as 5b, star as 5c, and so on. Again, I am repeating it. When you say capital A, it is I am saying C1, right? That is for our notation purpose. But internally, how it gets stored? It gets stored as 1100 0001. Similarly, when you say small a, it is getting stored as 1000, which is nothing but 8, and 0001. So you may ask, okay, when 81 is stored like this, which is this value, how does the system know whether it is a small a or it is number 81? That is purely interpreted by the program. When you fetch this value 1000 and 0001, if you load it or if you copy it into a character, then it will say, okay, you are a small a. If it gets stored into a offered, it will say you are 81. The memory itself doesn't know whether you are storing a character or storing a number. Similarly, when you go to numbers like 0 to 9, for example, you want to give a mobile number. It is like almost like a character, right? You are not going to do any kind of a transactions, or you are not going to do any kind of a numerical processing on the characters or on a mobile number. So it will get stored as a, we will store it as a characters, or somebody's okay, so somebody's zip code or something like that. In that case, the moment you define a number as a character, what it gets stored internally with starting with a capital F for F5, F6, F9. This is what we call abcdic format. Again, when I fetch it, F1 could be some totally different value. So whether that going to be the one character or it is going to be some other value depends on to which variable you are pulling into, and that is defined in the program and that is not defined in the storage. So let us think a little bit about the signed values. I said here storing signed values, but in reality when you are storing, the G system doesn't know whether you are storing a signed value or unsigned value. It doesn't even know whether it is storing a integer or a character. Everything happens in the program. The system is just storing zeros and ones, and that's it. It doesn't know whether you are even storing a instruction or whether you are storing a data. All that happens in the program, or maybe your CPU will interpret it, but not the hardware by itself. If a signed integer left to most bit is 0, it is a positive, and if it is 1, the value is negative. Okay, I know this looks a little complex, but I will try to explain you in a 2 3 different ways. Let us assume here that you have a binary value here, all zeros in the end 1 you have, and this is 2 power 0, which is 1, and rest are all zeros. The value, total value is 1, right? Why? Because this is 2 power 0, which is 1. 1 into 1 is 1. The rest are all zeros. If you add it up, you get a value called 1. let us say here I have a binary value all ones. Ideally, we assume that this is going to be a very large number because these are all ones. But let us do a mathematics here. 2 power 0 is 1, so 1 into 1 is 1. 2 power 1 is 2, so 2 into 1 is 2. 4 into 1 is 4. 8 into 1 is 8, and so on. And because this is a sign bit, we are going to say this 128 is not a plus 128, but this is a minus 128. Why? We just now said if the leftmost value is 1, then we will consider that as a negative. So minus 128. You add up all these values, what we will get is minus 1. So interestingly, a 0 followed by 1 is a 1. And if you look at all ones, that is not the number which you are expecting, 65,000, whatever number you are expecting, not that one, but it is a minus 1. Why? Because it is a signed integer. Okay, I will try to explain you in a little different way also, but time being, understand all the ones are minus 1. How? We put a negative sign at the end and we added up all these things and it became a minus 1. So minus 1 is 2's complement of 1 and 1 added to it. How that will happen, I will explain you in a minute. But when you say 2's complement, what does it mean is that wherever it is 0, you make it 1. Wherever it is 1, you make it 0. For example, here is the bit, here is 0, we made it 1. Here it is 0, we made it 1. Like that, wherever it is 0, we made it 1. And where it is 1, it should become 0, right? So 2's complement of this value is 1, 1, 1, 1, 1, 1, 1, and 0. And then we added 1 to it. So the last bit became 1. So 1, 1, 1, 1, 1, 1. So once, if you take a 1 and if you look into binary format and make a 2's complement of it, it will become 2's complement, and add a 1 to it, it will become minus 1. I will explain again in the next slide, maybe a little different way. Okay, so let us look at one more time. Plus 1 is all zeros followed by 1. Now we are creating a 2's complement. That means flipping all the bits. 0 became 1, 0 became 1, and 1 became 0. Now I add 1 to it. Then what will happen? All this is 1 and last one is 0 plus 1, which is 1. Okay. So all ones is minus 1. Similarly, let me look at the number 127. 0 followed by all these ones is 127. When I'm flipping all my bits, what will happen? 1 followed by all these zeros is my 2's complement, and I add 1 to it. So what it will become? 1, 0, 0, 0, 0, 0, 0, 1. This is minus 127. Again, if you really notice here, if the last bit is 1, it is becoming a negative value, and first bit is 0, then it is becoming a positive value. So this leftmost bit you look into, if it is 0, it is a positive value. If it is 1, it is going to be negative value. If I remove 1 from this, okay, if I make this 1 to 0, right, this minus 127 minus 1 is 1 followed by all zeros, which is nothing but minus 128. So every time you have to convert a positive to negative or negative to positive. Basically, you look this way. What you need to do, you need to flip all the bits and then you have to add a 1 to it. If the last bit is 1, the value is negative. If it is 0, the value is positive. The maximum value of a signed integer in a byte is 127. We have seen it because the moment you make it 1, it will become negative value. The minimum value is minus 128, which we have seen here. So 1 followed by 7 zeros is minus 128. If it is not a signed, and the same value, if you take it, it will become 256. Why 256? Because 2 to the power of 8. You have to remember this. The last bit is 0. It is positive, if it is 1 it is negative. And most of the instructions like L and A and whatever we use it, they all assume that the integer is coming is a signed integer. So let us do this in hex. We are spending a lot of time on this because this is a little tricky subject. Let us notice this. If the last bit is 0, then the hex value is anything could be 0 to 7. And if the last bit is 1, the hex value could be 8 to F. So the moment you see a value, a hex format, if you see 0 to 7 as the last nibble, if you can call it, the value is positive. In hex format, if you see anything from A to F, in the first value it is negative. Okay, so if you, for example, I have given here 7 a. What is that? 7 is between 0 to 7, so it is a positive, so this is the value. And 8 triple A, which is a negative value, which is minus 300038. 7 triple A is 31370 and 8 triple A is minus 30038. So this is an easy way of remembering it. The moment you see the last one, like you have seen here, 7 triple A, the last one is 7, also last one is 8. 7 is positive, 8 is negative. So continuing again, I will try to explain one last way and we'll stop here after this. For example, you saw me taking 7a, right? Let us do a 2's complement of it. So whenever you are doing a 2's complement, you are making 1 as a 0 and 0 as 1. But here we are using the hexa. So what we will do, we'll put a f's in the top and we will say f minus a is 5. F is in our decimal way. If you look at 15, a is 10. So f minus a is 5, f minus a is 5, f minus a is 5, and f minus 7, which f is nothing but 15. So 15 minus 7 is 8. Then I will add a plus 1 to it, then it will become 8556. So 7 triple A is 31370 and 8556 is minus 31370. You can go and do the maths like 16 power 0, 16 power 1, 16 2, 16 to the power of 3, and you multiply with 15 and all that mathematics you can do. 7 triple A is 31370 and 8556 is minus 31370. Similarly, in the previous example, we have seen 8 triple A is minus 30038. Let us take this again. 8 triple A. I put F's on the top. F minus A is 5. That means it's basically your 15 minus 10, which is 5. Basically, you are creating a 2's complement here. Then F minus A is 5, F minus A is 5, and F minus 8 is 7. So 7 triple 5, and I'm adding a 1 to it, and it is becoming 7 triple 5, 75556. So 8 triple A is minus 30038 and 7556 is 30038. We will prove it in one way and we'll stop there. 7a is 31370, 7 is 0111, A is 1010, A is again 1010, A is again 1010. 8556, 8 is 1000, 5 is 0101, 5 is 0101, and 6 is 0110. What we will do, we will add these two. 0 plus 0 is 0, 1 plus 1 is, no, not 2, okay, 1 plus 1 is 10. We shouldn't call it 10, actually we should call it 10. We were taught in 6th standard 1 plus 1 is 10, so you put a 0 here and you put a 1 here. 1 plus 1 0, 1 plus 1 0, like that you keep on going. Finally here also you will have 1 plus 1 0 and you will go 1. So if you really add these two things, it is 1 followed by all these zeros. But we are talking about only 16 bits here. This will get discarded and this will lose it. So what will come is 0 0 0 0. If you really notice it here, you start seeing there is a pattern here. Where is a, except this last two bits, which is same value. Wherever there is a 0, it became 1, or wherever it is a 1, it became 0. You can add these two, which is 7, 8, 5, 5, 6, and continuously if you do it, everywhere it will become 0, because everywhere you are getting 1 0, and finally the 1 goes here and the 1 will get discarded, and that is how the whole value will become 0, adding 7 triple A and 8556 leading to 0. So we spend good amount of time on storage. We are not, as I said, getting into what is a physical sequential file or what is a PDS, what is VSAM, like that. But we went into little inside the memory, how memory gets organized, how data really gets stored in the memory, and part of it is true for the registers or the storage. Now let us move on and start spending few slides on the CPU. Now we have moved into CPU. There are many components here which you will see here, but what we will mostly concentrate going forward will be the register set and the PSW, because this is register set is where the data gets moved in, moved out, as we have seen in our very first instruction LR1 num1, where the value num1 which is in the memory is getting loaded into the register R1. So we will spend a lot of time trying to understand this. Every time a operation happens, the data gets uploaded in the PSW. PSW you can consider as a dashboard at any point of time. Let us say it's like your odometer. It is showing how much speed you are going, how much fuel you have, things like that. So this is your dashboard. We are going to spend a lot of time on this as well. Beyond that, these are instruction registers where the instruction is there, and control unit, then ALU, which doing the arithmetic and logic unit. If you have seen any other CPU, this is not very different. In fact, everything starts here and lot of things got followed from GOS operating system itself. Now we are getting into registers. As you can see, there are four types of registers: general purpose register, access register, control register, and a floating point register. The purpose of each of these registers is different, but what is very important for us is the general purpose registers. We are going to spend some time in it, but when you are looking into the previous chart, there is a something called register set. We said all the registers are part of that. As I said, we will concentrate mainly on the general purpose registers, because that is what we are going to use in our program apart from the PSW. Here we are, all the 16 registers R0 to R15. Earlier in the programming convention, they just used to say 0 or 15, and later on they made it like R0 or 15, but both will take it to same thing. There are 16 and each one of them are 64-bit. They are divided into two 32 bits. So total will be 64 bit. What is they do? They used to hold the data, address, parameters, intermediate results, and so on. Okay. And technically, if you look at, all the registers are same. When you say hardware point of view, does the register 0 will be different from register 15? No, all the registers are absolutely same from a pure hardware point of view, but we are using certain convention, if you call it, or certain coding standards which we are consistently using from long time, last 40-50 years, and that's what IBM's book says. So the manual says, so we are following that, and that is why you are seeing here different registers doing different purpose. Can R14 can do what R15 is doing? Yes, technically it can do it, but we are following certain naming convention and certain methodology. R1 is where the parameter list register. It is commonly used to pass the address of parameter list to another program or another subroutine. R12 base register. This is something we will use extensively going forward. In fact, R15 is a base register, but when we convert it R12 as a base register, I will explain it later. Base register is commonly used as the register that contains the starting point of the starting address of any of the program that we are loading. R13 is save area pointer, usually points to the current program save area. The save area chain helps identify the calling program and previous execution environment. R14 is the return address register, typically contains the return address to which control returns after a call routine finishes its execution. So you are called from somewhere and you done the execution and you know where to go back. That is what R14 will tell you. And R15 is entry point or return code register before a branch and a link. It commonly contains the entry point address of the program being called. So R15 basically containing the address of the program that you are supposed to call, and R14 is containing the address from where you are called. Okay, and as I said, they are 64-bit and they play a very critical role in our entire program. Let's open one of the registers. Let us take it for example R14. This is a return address register. As I said, all the registers are 64-bit, but the address itself will be only in the low order 32 bits, high order will be zeros. Now you will ask a question, okay, if I'm not using the 64 31 to 63, why are there? The reason is the evolution. If you look at the GOS system, it moved from 24-bit to 31 to 64. What is making these programs run in 2026, 2027, 2028 that were written way back in 1950, 1960 is the backward compatibility. Anybody, any of us who are using a phone, let us say you take a iPhone, and you what happens is that there is a compatibility. You buy a iPhone, it keeps on upgrading the operating system to a point, and after that the phone says the hardware, I cannot upgrade the operating system any further. Similarly, there are a lot of apps that we designed, we have built. These apps also will say, okay, after a point on this software, I can run only on so and so version of the iOS. If I go any further, I cannot. That program has to be upgraded. That means that it is not backward compatible. What IBM's done, especially in the GOS systems, is fantastic thing. It is a backward compatible. So initially, when you have written a program in 24-bit, and when you got upgraded to 31-bit, whatever programs are there in the 24-bit can still run on 31-bit. When you have written programs in 31-bit and you have moved to 64-bit architecture, still the programs that are running in 24-bit and 31-bit architecture, the programs that is designed at that point of time are still running on the 64-bit. That is the beauty of this entire operating system. That is why it is here from last 50, 60 years. So very strategically it is using the low order 32 bits. Yes, there are commands which use the entire 64-bit, but when it comes to registers, we are using this 32-bit here, and the other higher order is 0. So the address is the whole thing, 000 whole thing. Low order 32 bits is actually return address, but this whole thing is your address. But program knows that my real address is lying only in the bottom 32 bits. Okay, and the design supports the full 64-bit architecture while maintaining the backward compatibility. So what does the R14 does? As I said, it is a return address register. So when a program is called, I'm saying, oh, I'm called from so and so program, and I'm storing that value in R14, and in the end I'm telling you branch back to return back to the caller. This is the example of one of the registers. We will see this future, but remember that the address, most of the time there are commands which will use the entire 64-bit, but most of the time the last 32-bit only utilized. First 32 bits will be broadly empty. And why this is basically, it is zeros. Why this is happening? This is happening to ensure the backward compatibility of the programs. Here is the PSW which we are talking all along. This is 128-bit, unlike our registers which are 64-bit long. If you look at it as from 0 to 127, the higher part of it, that is 64 to 127, is instruction address. Instruction address of what? Instruction address of the next transaction that is going to happen. For example, you have an instruction called A, B, C, and D. If instruction B is getting executed right now, it will go and pick up the address, not the actual instruction, address of the instruction C, and it keeps it ready so that when the actual sequencing, actual performance happens, execution, it will pick up that particular instruction from that address and it loads it. We will see it in the next slide. The 0 to 64 is having multiple kinds of values, and if you look at, there are different kinds of control bits are there, condition codes, program mask, addressing mode, and some other controls. What we are interested only is in this three. Condition code, when the condition code is set, any type of algorithm where a subtraction or something like that, addition, subtraction, something like that happens, or a logical happens, something like A is greater than B or A is less than B, things like that. Depending on the outcome, the condition code is set. For example, if you have done a subtraction and the value turned out to be a negative, the condition code will be 0, 1. Similarly, you compare two values and the first value turned out to be lower than the second value, condition code will be set on 0, 1. The condition code itself will not do anything in the program. That is something you need to write in the program, saying if my condition code is this, then say I have withdrawn more money than I have, then my value became negative, then I should get a message saying that you don't have enough bank balance to withdraw the money. So based on the condition code, there are times where within the program you set masks. Based on the mask, certain execution will happen. I will talk about it when we come to the branching and jumping section. Similarly, beyond the program, there are certain masks that within the PSW we put, which are called program masks. There are only 4 specific masks. Again, we will discuss them in branching section. And when this particular condition code happens, for example, let us say overflow happened, which is 1, 1, and if my fixed point overflow mask is on, then something will happen. The event will happen. Maybe the program will discontinue and give an error message saying that hello, fixed point overflow has happened. If my overflow is condition is set, that means 1, 1 happened, and my last bit, which is 2, 0, is on, then see if there is a significant overflow, then that particular message will come saying that okay, the program is abandoned, or because there is a significant overflow is happening. I will talk about it in detail in that branching section, but just think that this is something which we are going to use. Then there is a addressing mode, bits 31 and 32. If it is 0, 0, that means program is running in 24-bit addressing mode. If it is 0, 1, it is 31-bit, and 1, 0, 64-bit. If you have done any COBOL programming, you would have done A mode and R mode. Basically, this is nothing but the A mode. And not many times we use it in our programming, but just to nice to know that there is a way the same program can be run maybe in 24-bit or maybe even a 31-bit. So which mode it is running, that is set in this particular bit. This is the PSW. In this, mainly we will use this conditional codes, which is 18 and 19, and we will also have a peep into instruction address in the future when we are doing actual programming. So we are going to put this all together, like as I said in my previous slide. Once any instruction gets executed, the PSW will get updated. As I said, this is like a dashboard. So what is set? Most importantly, the condition code is set, and the instruction address of the next instruction is already sitting here. So what will happen when it goes back here, right? And the fetch instruction from the storage will happen. So when you, if let us say this is a starting point, you have an instruction address of the next instruction, and you go to that address and you pick up that particular instruction from the memory. Then you load the instruction into IR, which is the instruction register. Then the control unit is there, which will decode your entire instruction. Okay, I'm doing a load here. I'm taking a num1, which is from the memory. I'm putting into a R1, which is a register. So it decodes and it keeps giving multiple instructions to this ALU and the register set. ALU will do you actual arithmetic operations like addition, subtraction, and all that. It will also does the logical operations. That is why it is called ALU, which is nothing but arithmetic logical unit. And when it is doing it, it has to store the values somewhere, and where it will store the values, it stores the values in the register set. That is what we have seen in when we say R1 register 1. Similarly, all the 16 registers we have seen, which are the general purpose registers. So data keeps getting stored in those registers, and ALU keep talking to those registers because they're immediately available to ALU. And once the instruction is completed, again the PSW gets updated. So this is the loop that keeps going on from the instruction to instruction. So one more time, PSW holds the address of the next instruction, contains status information like CC, mask, control bits, and all that. Then use IA from the PSW to access memory. IA is instruction address. It is there in a so and so place. Pick it up from there. Instruction is read from the storage. It gets loaded into IR. Instruction is placed in instruction register. Now ready for the decoding. Who is doing the decoding? Control unit interprets the instruction. It determines the types of operation it is supposed to do, and it keeps sending the messages to this ALU register set. ALU operation happens, data will move, it can do branch, it can do jump, it will access memory, etc. Basically, the between the ALU and bit register, whatever operations that you are asking it to do, the arithmetic and logical operations, that will happen. Once you have done the operation, again you have to give back the status. So status is set in the PSW, and since this instruction is completed, you are already pulling up the next instructions address, and you are keeping it in the PSW. Okay, I will show you in a different way. Same thing. Let us assume that these are my actual instructions. L R1 equal to x20, A equal to R1 equal to x21, whatever it is, str1 x22, whatever. These are my instructions. These are my assembler instructions, and we will look into it how this became 58102000 and all those things. We will look into after some time when we are doing the class 2. But this is the actual, let us say, your executable code. Where is this instruction in the memory? It is at 1000. This instruction is at 1004. This instruction is 1008, and this instruction is at 100C. This is the content of the instruction, and this is the address of that instruction. So what is happening that first you will do a fetch. So in PSW, the very first instruction address is there. If you look at this 1000, this is the address. The actual once you fetch it, what is getting loaded is this 58102000. This is the actual instruction. This is the address of the instruction which you are seeing here, and this actual instruction got fetched from there. It moved into IR instruction register. Then this, basically this operation is nothing but this is representing this operation. This operation happened, PSW got updated, and what is PSW now doing? It is trying to get the next address already in the system. For example, 1004 is the next address. Again, 1004 is read. Okay, I have this particular instruction here. It has come here. It goes into IR. Instruction got executed, and by the time I'm already ready with my address of the next instruction, which is 1008. This is the again address. This is the actual instruction which got into first into memory, then it got into loaded into IR. This instruction got executed and again moved to next address, which is 100C. Here what is happening, 100C actual instruction is 07F0, which is nothing but branch to say 1000, 07F0. So branch to 1000, that instruction is happening, and next instruction address is 1000, which is but nothing but first one. That means basically this is a loop. Let us say this is gone into a loop. So that is what it is happening. You understand, PSW gets the address of the next instruction. First it loads into the memory. From the memory it loads into IR. Here it talks to ALU and registers. It gets executed and the condition code is set, and the address of the next instruction is already stored in the PSW. This keeps going on until you end the entire assembler program. So same thing in a little different way we are showing here. This is the CPU we spoke about, the control unit, the registers, and the ALU. ALU is where all the arithmetic logical unit where all the operations are happening. Register is where your data is there. Control unit is like what you can call as an orchestrator. It is making the whole thing orchestrate. You have a storage here where the values are there at address of 100, 104 and 108. Maybe its content is 10, 20 and 30, and you do this R1 num1, R1 num2 and R1 result. This is the what is actually getting executed. I will hold on for 10 seconds. You spend some time to understand it, because we are going to move to the next topic after this. Okay, so we spent a lot of time on storage. We spent a lot of time on how CPU works. Let us pick up 2, 3 small topics, and then we will wind up this particular first class. We will cover 3 more topics, small topics, but very important topics. One is base plus displacement. This is something you need to understand. It will be used extensively. Then types of instructions and tri-model addressing. Here we have a simple data structure, a record. You can call it say my report, and which is DSL40. And under that we will explain you later what is DS, what is DC. But right now remember this is a 40. Let us say in our COBOL it is a 01 variable, which is my report, and all the 05 report records are amp ID and so on. And it has various fields. The first field is a full word, that means it is an integer. Rest all you are see there. So these are all characters. So let us look at this particular record again. Employee ID, which is F1234, that means it is a length of 4. So it is starting at 1 and 1, 2, 3 and 4. Now there is a blank, so which is taking 4 spaces, 5, 6, 7, 8. Then again employee name, which is taking 15 spaces, 19 to 9 to 23. Then there is another blank 2, which is taking 5 spaces, 24, 25, 28. Now there is another full word that is here, and what is interesting in this place is this is a full word, and if you remember, full word should always start at a boundary of 4. So 4 into 8, 32. It cannot start at the boundary of 29. Remember this. So 24 to 28 is done. Ideally the next field supposed to start at 29, but that is not happening. Why? Because a full word can start at the multiples of 4. A half word can only start in the multiples of 2, and the double word can start in the multiples of 8 only. So why? Because a full word is 4 bytes. So what will the system will do? It will keep some blank spaces. It will pad it. That means there will be nothing here, and it will start at 32, 33, 34, 35 full word aligned, and then you have again a blank which is 36, 37, 38, 39, and then you have a 40 which is a gender, which is the last field. After this, what we will do, we will add one more column to this, where instead of saying my starting address starting point is 1, we will give a starting address called A000. We are adding address to it. Instead of saying 1 2 3 like that, we are assuming that this record is starting at A001 and its end address is A004, so on. Blank 5 is A005, employee name starting at A009, and so on. Till now it is fine. Here when we end up at A01C, the ideally emp YYYY should have started at A01D, but it is a good notation. In fact, the program will run. Sometimes the older programs will abend, but it is better you always force align it. That's why what we are doing in terms of DS0F, we are padding something there, and A01D to A01F, so that your full word will always start at the boundary of a 4 bytes. Okay, so it is starting at A020 and finally everything ending at A028. If you really look at displacement, the first one is no displacement. It is, that is where it is starting, so it is 0, then 4, 8, so on. So if you really look at 22 A001, the displacement is 1F, and then similarly the last one, the displacement is starting at 27. If you look at, this is the length, 4 plus 4 8, 8 plus 15 23, so on, if you can add it up. So in this case, if you assume that A001 is the base, then emp YYY will be base plus 1F. In other words, displacement is 1F. This is what we are going to use in our notation. Ah, Finally, something familiar. If you look at the top part, is the assembler record which we are looking at, and here is your COBOL code for you to make understand very easily. S99 comp value 1234. This is nothing but your full word. Then you have X4 which is initialized with spaces. Then you have X15 initialized with a name. Then again another X5. Then S99 comp, which is nothing but your full word initialized with 1980. There is a blank space. Then you have a gender value after that. Okay, so I hope it's slowly started falling in place and it is making sense to you. I have changed a few things here. What is in the red? Earlier this used to be a full word. Now I made it a half word, and I also added what is called a packed decimal. Let us see how this translates into COBOL program, or you can come other way around. Half word is pick S94. Remember, in the COBOL, what are the ranges for full word, half word, and so on. So pick S9 for comp with a value starting with 1980. This is the your half word. Then what is a packed decimal? We will talk about a lot about the packed decimals, and handling packed decimals in assembler is a very complex stuff. We will come, or for one of the classes we'll only dedicate on packed decimals. But if it rings a bell, this is what it's in COBOL. Whatever we call it, comp3 variables with, let us say this is a 10 bytes. Pick S97 V99 comp3. Of course, it could have been initiated with this particular value. So to map it, right, you have a full word here, you have a half word here. These two are integers. So it is S99 comp and S94 comp. And here it could have been a decimal value. But in assembler it doesn't store as any kind of a decimal value. That come to the topic later. uh, but if you see something like S97 V99 COM3, in reality how it will get stored internally is this is called a packed decimal. So let's move on. Let us solidify this concept of base plus displacement. As I explained you, base emp id is starting at a triple zero and emp y field is at a020. So let us assume that we have just loaded this record into the register. That means A00 is the starting point. So register will say, okay, I'm at point 0. And where is my amp y? It is at a distance of 0 to 0 from me. It is like your Google Maps. You are going into a restaurant or you're going to a hotel and you will want to find out that where is this particular place, where is my office, how far it is, and when you try to measure it, what it will do a 0 point. What is 0 point? The hotel or a place you are staying right now, the maybe the airport is your 0 point, and from there how much distance this particular office is. So when you taken this whole thing and recorded and loaded into a register says my address by the way is C by R12. I'm putting in a register 12. What is the number 12 in hexadecimal? It is C. From C, something is at a distance of 0 to 0. So every instruction data is referred as a base, that is which register you are in, plus displacement. In this example, R12 is the base register. When program is loaded, starting point of the program is stored in register 12. Every other instruction is referred with its displacement. Okay, so that is why emp y is referred to as C020. So the first alphabet or first hex value is the register C020, where C is base register and 020 is a displacement. This displacement value is 12 bits. So if you put 1111 12 times, it is a 4K. So the it will can find out any address which is in the range of 4000 bytes. 4K relative to base register can be accessed, which is kind of sufficient for most of the operations. Then of course IBM came up with something called a 20-bit register. How do you do it? It is based on your instruction. There are instructions which will use a y, and where you know that okay, I'm using a long displacement and not the short displacement. So in those cases, there is a terminology. I don't want to confuse you. Above the line, below the line, above the bar. Basically below the line means 4K, above the line means up to 1B, and above the bar means up to 2GB. So for displacement, we have a long displacement with 20-bit that can be accessed up to 1 MB range from base register. There is also 2GB, which is, we call it generally is a above bar. The program selects the instruction type while the assembler and hardware handles the address calculation. You don't have to worry about how addresses are calculated. The moment you compile a program, there itself you start seeing that every variable has been assigned a particular address, and it is also at a certain distance from the starting address. When the program gets loaded into the system, it will know that okay, my starting point is here wherever I'm entering. We will talk about C sect and all that in the next class. This is my starting point. From the starting point, this is where the address is. So all that calculation happens internally. You need to understand this concept that when you are looking anything like this C020 or A011, whatever it is, or E0 something, understand the first one is talking about which register it is sitting in. It is like the hotel you are sitting in, and you can access only certain amount of distance, which is the 4K if you are using a 12-bit displacement, and up to 1 MB range if you are using a 20-bit. Of course, there is a much larger one, which is a separate topic. Understand this part, then understanding the code will become very easy for you. Another quick concept we are introducing here, you would have by now observed that data is moving from register to register. right? When there is some calculation happening, let us say we use it in our calculation always R1, but there could be R1 and there could be a R2 or there could be a R3 in that. So data is moving from within the register and this movement is happening within the CPU. Then you also notice that data is moving from memory to register. Like when I said load R1 num1 which is sitting in the memory is getting loaded into the register. And when I said store R1 to result, that means data is moving from result which is in the R1 which is in the register into the memory. Similarly, data can move from memory to memory. You may say, okay, how this is happening? For example, you are copying that my address, my billing address and my delivery address both are same. You just want to copy that. Then what will happen? The address is getting copied within the memory. There's no calculation here. There's no arithmetic calculation here. There's no logical calculation here. So there's no reason for it to come all the way to ALU and something to happen. It is just a byte to byte copying happening. So the data is moving from memory to memory, and this is happening within the storage. So within the CPU, within the storage, between the CPU and the storage on both the ways. So you keep hearing this particular nomenclature that this is a RR instruction, that is register to register. So arithmetical logical operations will happen. Register storage, some of them like you will see shift, multiple registers, branching and all that will happen. RX instruction, so the instruction which we are trying to load a data from your memory to register is like this. We call it RX kind of a instruction, load and store. Then SS, which is storage to storage, move edit strings. Why I want to introduce this, because you keep seeing this in a in a literature a lot, but otherwise if you understand the instruction itself, you don't have to worry so much to know what kind of type instruction it is. But many times you see in literature, oh, this is a RX type of instruction. So understand this. There are four types of movements happening, and based on that there are a few more also, but this is the most important one. So one more small topic, trimodal addressing. As I said, the machine supports three addressing modes, 24, 31 and 64. Initially when S360 came, it came in 1960. The address was 24 bits. Please remember, it was a very long time, right? 40 plus 20 to 60 years back. At that time storage is extremely costly. Every single bit matters, and that is why the whole cost of the computer was basically its memory. So 24-bit address we started in S360. Then it moved to 31-bit address, which is 2 GB. If you look at 2 into 2 to the power of 30, which is 2 GB, this has come in S370 systems, which came in 1970. Then you moved into 64-bit address, which is 16 EB exabytes, which is came in 2000. The mainframe can work in all the three different addressing modes. Okay, this is different from base displacement calculation. Don't get confused with this. In a way, in a nutshell, if I can tell you, let us say base when the moment you load a program, and it will say, okay, what is my starting address, and what is in the end, it will say my starting address plus displacement. The starting address plus displacement value, in our case we have seen like A020 or A0, maybe next one A024. What is the maximum value that can stay in that address is basically defined. 16 MB is something you can have in a 360, then 370 it become 2 GB and it becomes 16 EB, which is of all practical purposes it is infinite. Okay, 21, 31, 24. You may say, why not 32? There is a logic behind that. Why only 31 and not 32? Because the last bit is made 0, and 64-bit modes define the CPU's overall address size capability. We have seen this is in PSW. There are two particular bits which will tell the system whether it is running 24 or 31 or 64. Again, don't worry too much about it, but just understand there might be very old programs which are run only for 24-bit address mode, so they can run only there. But most of the programs today you can run anywhere. Just a small um, tidbit here. What is 5 exabytes? All the words ever spoken by human being. Someone said this. So every single human being ever since in this world, I don't know how many million of years ever since spoken is 5 exabytes. So think of how much when we say 16 exabytes. So as I said, for all practical purposes, it is infinite. I also spoke a lot in this class. I didn't expect that this will go all the way up to 1 hour 25 minutes. And if you come all this way and you're listening this training till now, then you would have become an expert in assembler. Thank you. I will show one more slide, which is summary of everything we had so far. Once again, thanks for listening to my training. So what we learned, we try to concentrate on the architecture, not so much on the programming language per se, memory organization, how bits, bytes, and so on, what is a off word, full word, and how much space they occupy, how negative values are stored and interpreted. We studied a little bit about registers, all the 16 registers, and we also studied about the PSW. Then we spent some time on taking one of the simple record, employee record, and how it looks in a assembler and how it looks in a COBOL program. We studied about the concept of base plus displacement, and there is a tri-model addressing. I spoke about 24, 31, and 64 and different types of instructions. Let us put this in a little graphical form. Here it is, everything in one place in a graphical format. Memory organization, offered full word concepts, negative values. We spoke about registers. We spoke about the PSW, a base plus displacement, tri-model addressing 24, 31, and 64, different types of instructions and instruction formats, RR, RX, and all that. And it is given little bit of the structure and some example description here. If you want, you can take a printout of this particular slide and stick it to your board or wherever you are working. That will help you a lot. Thank you. And let us go to class 2, where we're going to talk a lot about integers and adding and subtracting. And let us start getting little deep into the instructions. Thanks once again. You made it. Thank you very much.